Hello and welcome back to this series of lectures on control systems uh, for the course on electric vehicles. So we'll continue our discussion on state space methods. So where we had left off last time was uh, we could check the conditions for controllability of a system, and once the system is controllable, we had defined certain objectives which we could achieve via pole placement. So one of the requirements of the control design there was, so we started off by writing down our control law as u equal to negative of kx, which means that we assume that x is continuously measured. So in some cases, so x here are the states. So if I look at say a DC motor, I assume that I am measuring the position, the angular velocity and the current. So in some cases it may not be able to measure all the values, and therefore my x is not readily available. So what happens if my states are 3, but I can only measure 1 at the output. So I am looking now at systems of the form x dot is ax plus bu and y is cx. Okay, so let's right. So in the pole placement approach to design of control systems, we assume that all state variables are available for feedback. Again, in practical systems, you will only have few outputs which are measurable, right. So speed in a DC motor, I may not be able to measure positions or even currents, and some may physically be unmeasurable also. So we ask ourselves a question, so is it possible to estimate the unmeasured state using the measured data in terms of the output? So there comes in the notion of observer, where observers, they reconstruct the unmeasurable states so that I can apply state feedback control. And we'll also conclude our series of lectures on control systems by look at what happens if there is a measured noise, right? How do we design things called the Kalman filter and so on, right? So okay, so that gives us to the notion of observability, and we'll quickly run through this. So the notion of observability, mathematically it's the dual of controllability, and it now answers the question of what if all the states are not measurable. So observability deals with the possibility of estimating or observing the state of the system by just knowledge of its just outputs, right? I don't even maybe need inputs for the system. The system is observable if for any x naught, any initial condition, there is a tau such that x naught, the initial condition, can be uniquely determined from ut and yt for when I observe my inputs and outputs, largely outputs for a given period of time. So if the initial state vector can be found from ut and yt measured over a finite interval of time, the system is said to be observable. Otherwise, the system is said to be unobservable. And observability refers to the ability to estimate a state variable. So, okay, let's see this concept with the help of an example. So the circuit here has two states. I have the inductor current, the capacitor voltage, and let's say there is no input. If u is 0 and x2 is 0, and say x1 is some non-zero value, then the output is identically 0, right. So the output, and say I am just measuring y as x2. Now any x naught which is a and 0, and for ut equal to 0, everything will yield the same output for whatever values of a. So there is no way to uniquely determine the initial state, in this case a, and therefore the system is rendered as unobservable. Okay, what does it mean, right? So I look at my state equations. This was a solution from which I could deduce controllability, and observability. Well, I look at what the output equation is, right? So it focuses on determining x naught from the output yt Okay, so because it's only related to these two things, I can maybe ignore the effect of inputs, which I can just add it on or add or subtract a little later. Okay, so now I deal with this equation. Again, what is, I can measure the output, so I'll assume the output is known from measurements. C is the given system matrix. I know how to calculate e power at, that A is given. So again, I have an equation in the unknown x naught. So I do a little bit of matrix algebra and ask myself a question: when does a solution x not exist? Okay, so a system is said to be observable. I again start with the definition: if every state x t naught can be determined by the measurement of y t over a finite interval from t naught to t 1, right. So, which means that whenever the system is completely observable, if every transition of the state affects every element of the output vector, right. So, mathematically this would mean that now I am looking at a situation where I need to find out x naught, and that boils down to looking at the rank of what I call now as the observability matrix. Again, we will not go too much into the details of this. You can just write down for yourself these expressions as a set of linear equations, but this is a condition for observability, that the system is completely observable if and only if the rank of the observable matrix is n, right. So, there is a little duality between controllability and observability, which means that if the pair A B is controllable, it means that the pair A transpose B transpose is observable. Similarly, the duality also says that observability of a pair A comma C can be tested by looking at the controllability test of A transpose C transpose. Again, okay, this is just a small passing remark in this case. Okay, so how does this look like, right? So, I have a system where matrix A is of this form, matrix C is of this form. I quickly compute the rank of the matrix and see that the system is observable, because the rank of the observability matrix is 2. Okay. Now, in the above example, if I just do the state space 2 transfer function, what I get is okay, so I have a system of the form s square minus 2m. So, the system has 2 states. I see there are 2 poles of the system here. There are no pole 0 cancellation, indicating the system is therefore completely controllable and also observable. So, I do not lose any poles or zeros during the cancellation. Okay. Now, similarly, now what I do is, instead of b being 1 comma 0, let us say I have my input entering through the x2 term, right, and the c remains c is now 0 1, b is 0 1 transpose, and the transfer function of the system now will have only one pole here, 1 over s minus 2, right. So, note that there is a pole 0 cancellation at x equal to 0, indicating that the system is either unobservable or uncontrollable, right. The rank of the observability matrix is given by 1, and therefore the system here is unobservable. So, whenever we lose controllability or lose observability, there will be a pole 0 cancellation in the system. So, we can maybe quickly check if the system is controllable or not. So, when b is 0 1, a times b is 0 1 0 2, my b is 0 1, this will be 1 and this will be 2. Well, the system is actually controllable, right. So, 0 1 1 2, right. System is controllable, well, but the pole 0 cancellation now affects the observability of the system, because the rank of this is 2, rank of C is 2, and therefore the system is controllable, but it is not observable. Okay, so now back to why are we designing this, right? We need to implement u equal to minus kx, and in that implementation sometimes all the states are not available for measurement. Okay. Now, I know the notion of observability, and we say, okay, that can I get the initial state based on certain measurements of the output from some initial time to some final time. Okay, so the notion of observability, why is it completely sufficient? The standard notion of observability provides only value at a particular instant of time, instant maybe some kind of t naught. Okay. Now, when I say u equal to minus kx, I'm not just happy by taking x at t naught, right? I need continuous estimates of a state. I need continuous estimate of the states. So, just by measuring maybe the speed, can I get an estimate of the theta and the current, right? Now, this state observer estimates the state variables based on the measurements of the outputs and control variables, right? Now, we will use the notation x tilde to denote the observed state vector. In many practical cases, the observed state vector is used in the state feedback to design the control vector. Okay, so what does all this mean, right? So this is my given system, right? And now I consider a copy of the original system, right? So here x hat is my estimated state, okay, which I can only measure one of the outputs. I can measure maybe the speed of the motor, but I am also trying to estimate with it the position and the current. Okay, so this is the estimated value, this x is the original value. There will be a error in this definition. Okay, now taking derivatives of this, okay, I just skip a bit of this part. So E dot will be a x cap dot minus a x dot. So it's simple to see that E dot equal to A. If A is a stability matrix, right? So what I want is that E must eventually go to 0. So if A is a stability matrix, which means that all the poles of or all the eigenvalues of A are in the open left half plane, then the error converges exponentially fast to 0 for every u, right? I am not really worried about what the input here is. Okay. Now, the problem happens when A is not a stability matrix. Well, when A is not a stability matrix, we need a closed loop estimator now, which looks something like this. So I have A x hat is BU. I introduce this error term in the output ke y minus c x hat, or x hat dot now becomes A minus ke c bx tilde bu and some ke y. Now, here x hat is the estimated state, c x hat is the estimated output. The inputs to the observer, if you look at, are the output y and the control input u, right. The matrix A here is now called the observer gain matrix, just like u equal to kx was the controller gain matrix. U equal to this ke here will be my observer gain matrix, right. Okay, the matrix ke is the observer gain matrix. It is a weighting matrix to the correction term involving the difference between the measured state and the estimated output, right, or measured output and the estimated output. Now I look at what the observer error is. Now the observer error is now again x minus x tilde, the observer error. So and then E dot now becomes, with some simple manipulations, A minus ke times c. Recall the expression of a state feedback. You had A minus bk times x. You could design this k to make, of course, A stable if it is not unstable, assuming the system was controllable. And if you also want to place poles at some desired locations, I could design an appropriate k, right. So in this case, if A is not stable, I can design an appropriate ke to make the system make A minus ke times c stable, and therefore my error converges to 0. Right. So if the eigenvalues of A minus ke are chosen in such a way that the dynamic behavior of the error is asymptotically stable and is adequately fast, then any error vector will tend to 0 with some adequate speed. Now the observer gain ke, right, can be determined to yield the desired stability matrix. Of course, when can I do this? When could I do A minus bk? I could do if and only if the system was completely controllable. In the same way, I can now do A minus ke times C if and only if the system completely observable. Okay, so those details we can kind of skip for now, but we'll assume that the system is observable for our design purposes. So if I am given a system of this form, I can first check that the system is fully observable, and if I assume that so now A minus K E will have some eigenvalues. A is given to me, C is given to me. If I choose the observable observer matrix poles to be at -10, I can design an appropriate K which will place the poles accordingly. Okay, so it's just a standard process. In the same way as I design my A minus B K and just look at the desired characteristic equation and map it to the characteristic equation with the unknowns in KE1 and KE2. I just equate the coefficients, compare the coefficients, and I can design an appropriate KE matrix. This is very similar to what we had earlier done in the case of pole placement. Okay, now what is the effect of addition of the observer? So in the pole placement design, I assume that XT was available for feedback. However, in practice this may not be the case, right? I may not measure all the states, but I can measure maybe some outputs as y equal to Cx. So we will need an observer and we will use the observed state for the feedback. So instead of u equal to minus Kx, now I am using u equal to minus K x hat. These are the observed states, and eventually the observed states will match the original states, right, based on the observer design over here. Okay, so the design process therefore becomes a two-stage process. The first is I determine the state feedback matrix gain K. So I assume that the states are available for measurement. I complete my pole placement design, and then I ask myself, well, is X measurable all the time? If X is not available for measurement, then I check for observability and then design an observer. So in the two-stage process, I first design the feedback gain matrix to yield the desired characteristic equation. This is again based on the closed loop performance, which can be mapped to the location of the closed loop poles. And second being the observer gain matrix to yield the desired observer characteristic equation. Okay, now how does my entire process look like? I looked at a control design first, then now I am looking at an observer design, right. So the control design, instead of u equal to minus Kx, becomes now u equal to minus Kx hat. Okay, what is my how does my closed loop look like? So this is Ax minus B K x hat. Okay, so I can just do some manipulations to write this in the form of x dot equal to A minus Bk times x plus Bk times E. How do the dynamics of E vary? E is simple, right? It was just the capturing the error dynamics between the actual state and the estimated state. Okay, so now I have a good closed loop dynamics which has the dynamics, or which includes the controller, the state feedback controller, and also has the embedded the observer into the design, right. So okay, this is just a little plot of the system that we just designed. See how the errors converge to 0. Okay, what happens when I add the observer to the system? So assume that the plant is completely observable. Also, assuming we use the observer state feedback control, then the equations for the observer are simply given by something like this, right. You have x tilde is the function of the x tilde itself, some y here, and then u equal to minus Kx, right. So the transfer function of the observer, right. So if I look at the observer, what does the observer do? The observer takes in the states y measured at C times x and gives as output my x tilde. Okay, so And then so if I look at what is the transfer function from u of s to y of s, that simply becomes an expression like this, right. So the effect of adding an observer is that, so I have the plant which gives me ys, I take this measurements ys, I feed it through an observer and generate the appropriate control input us to the plant, right. So know that the transfer function now acts as a controller for the system, and hence we call this us over minus, that this is the observer based control transfer function, or simply the observer controller transfer function. So this has both things in it. It's not just u equal to minus kx, it has the control part, it also has the observer part embedded into it. Okay, so I take a little example of how to do this this simultaneously. So first I do is I'm given a and a b. I want the desired closed loop poles to be at these two numbers, and suppose now I'm using the pole placement approach. This is now kind of straightforward by what we have learned. I can design an appropriate k that will place my closed loop poles at these locations mu1 and mu2. Okay, now using this state feedback control, so this is my control input. Okay. Now suppose that we use the observer based state feedback control instead of the actual state feedback control, right. So my output is only x2, I don't measure x1 and x2, I don't measure both the state variables x1 and x2, instead my y only gives me x2. So instead of using the actual state feedback control, now I use u equal to minus k tilde, and now I want to place the observer poles, right. I choose them a little far away from the controller control poles. So the desired observer gain matrix will be computed by the error dynamics, and I just do the same things as I do for pole placement. So what I get is ke is 16 and 18.84.6. Okay. So the observer based equation now takes this nice looking form, where I have both the controller and the observer design. Okay. So so the dynamics now can be described for individually for the plant, which has states x1 dot x1 and x2, and then I have my observed states which are x1 tilde and x2 tilde. Right. So the response of the system to the following initial condition, I can just plug in the equations and see how does my system response is to a given initial conditions. You see my error goes to 0, and states take values as desired. Okay. So in the example, I choose the control poles at minus 1.8 with for the negative real part, and -8 and -8 for the observer poles, right, and this results some kind of some appropriate control gains. So what I see here is that, so okay, so this minus 1.8 plus 2 is something here, whereas -8 is far away. So we note that the observer poles are placed far left of the controller. Now if I say, okay, why am I placing it so far? So what I want ideally is that, so u is minus k x hat, sorry, x tilde, where I have the estimated states, but what I want is my observer to quickly estimate the observer states and then feed it to the controller, right. So I do not, and for that reason I place my observer poles very far away, so that the dynamics are faster and I get the estimates faster. Okay. Now you say, what happens if I place them closer to the controller poles or the closed loop poles? So let's say I want to place the observer dynamics at s equal to 2 and s equal to minus 1.8 and compute the appropriate gains. So what I see here is that the response becomes very slow, right. So we do little more adventure, and then we say, okay, well, I will even place my observer poles to the right of the controller, and you see that the response is totally undesirable, that the response becomes very slow and so on. So in summary, so if the observer poles are placed to the right of the controller poles, the observer poles are slower than the controller, and then the estimation error takes long to decay. If the poles are placed close to each other, the observer tracks the system state but not significantly faster than the system itself, again leading to a delayed correction of errors. And therefore, I want to place my observer poles far away to the left of the controller with much faster dynamics, in which case the observer quickly corrects the estimation error, and therefore the state estimation decays much faster, and then I get u equal to I get the exact states for my feedback, which will give me the appropriate desired closed loop response. So, so this a little bit of material here for you to check where these lectures material for this lecture come from. 2 textbooks and one of my courses on control engineering in NPTEL. So, in the last concluding lecture, we'll just look at of issues in practical implementation of this state estimator. That's coming soon. Thanks for listening.